So now let's look at the mode for nanoimprint lithography. So the mode is also called template, stem, or master. So to avoid adhesion between the mode and the between the mode and the resist, between the mode and the resist. So we need to coat it the mode with called mode release agent. It is also called releasing layer or anti-slicking coating or anti-adhesion coating. So normally the mode is made of silicon or quartz, so those materials are easy to fabricate. And sometimes it's made by the metal, but recently polymer mode is more and more used. So the normal strategy is that, so first we make the mold into those materials, then we copy the mold into the polymer mold, then we use the polymer mold as the mold material to do the imprint. So then this way we can save the expensive silicon or quartz mold. For the imprint, so the feature is 1 time. That means, so the feature size, if this is the feature size, so the feature size is the same as the imprint mode. But this is different from the optical lithography. For the optical lithography, as we have seen before, so the feature size on the photo mask is 4 times that of the feature size of the final feature we want on the wafer. For example, here I give you an example. For the case of 65 nanometer features, for optical lithography, the feature size on the mask is 260 nanometer. For the imprint, the feature size is 65 nanometer. So the property for the mode, what we need, first, compatible to the mode release agent coating. This one is actually very, very critical because many materials, even though they have good property, mechanical or chemical property, they are not compatible with the mode release agent coating. Then we need the mechanically durable and chemically durable and low thermal coefficient of thermal expansion mismatch. So as we can see here, for the optical lithography, so because of the diffraction, we need to do with many tricks to improve the resolution. Here we have this optical proximity correction. Another thing we work on the most is the phase shift mask. So we also do the phase shift mask for the optical lithography. For the imprint, so we don't need optical proximity correction or phase shift mask. All we need, we make a mode that we can have very high resolution patterning. So here are the mode issues. So first, regarding the sidewall angle, so obviously, regarding the sidewall angle, so this one will be difficult. So when you do the imprint, it's very hard to separate. It will be like a stripped. This one will work vertical sidewall. This one will be easier for the separation, but this one you lose the resolution. The feature side on the bottom is different from the feature side on the top. But this one is obviously easy to detach the mold from the wafer. For the sidewall roughness, if the sidewall is rough, obviously this is not good for the separation. But this kind of sidewall, you see the ripple, wavy structure, like this, zigzag, wavy. But this is the typical profile using a deep RE. For the deep silica etching, let's use the Bosch process. We use this process. So when we use the Bosch process, we get this kind of wavy sidewall profile. For the mold, we have another issue is the polymer flow and filling property. As we see, if we have very big features, the filling may be a problem. Finally is the resist deform. You can see here the resist got deformed and the snaking problem. This is also a major problem. As you can see here, on the top side, the mold without anti-snaking, anti-adhesion coating, you get the peel off. The resist here got peeled off. On the bottom side, with the anti-snaking coating, there is no peeling off. So how to do this anti-snaking coating? So actually, this is the major secret for the imprinting lithography. So in the 1995, the professor Stephen Troch group from University of Minnesota, he asked a student to spend about 1 year to find how to make the mold very, very low surface energy. But he wanted to keep the secret. So when he published the paper in Science, he mentioned clearly that we do not need any mold release agent. But actually, this is wrong information. It's only the only purpose is to mislead people. As a result, other people they cannot duplicate the imprint after maybe 2 or 3 years. Then they realize that you need some anti-snaking coating on the mold surface to make it actually work. So this material is the most popular one for the mold treatment. This is called FDTS, perfluorodicyl trichlorosilane. Another popular material is called FOTS. So the only difference So this one, see, this is O. O. This one is octyl. Octyl means 8. This one is D. D is the dicyl. Dicyl means 10. So we have 10 carbon. This one we have 8 carbon. So we know that fluorocarbon, we know fluorocarbon gives you a low surface energy, but you cannot coat fluorocarbon onto the wafer surface. For example, the most popular fluorocarbon material is the PPFE, polytetrafluoroethylene. This will obviously give you very low surface energy. This is also called Teflon. But if you coat a layer of Teflon on the wafer surface, this will not work because the Teflon will not adhere to the wafer. So the Teflon film will not adhere to the wafer. So when you do the imprint, it will be peeled off easily. So to solve this problem, so we want, so one side, this is like a Teflon, fluorocarbon. On the other side, we have this chemical bond. When we have chemical bond, it will be very stable on the wafer surface. So how to do this process? So this molecule gives you this kind of coating. It's self-assembled monolayer. How does this thing work? So here we have this trichlorosilane. So we have this thing. We look at this group here. So trichlorosilane. So we have one silicon, and we have the chlorine. So we have silicon here, we have chlorine. For the wafer, silicon oxide, for instance, it's not hard to have the surface terminated by the hydroxyl group. So you do the oxygen polymer. You clean the wafer, you do oxygen polymer, then you have this hydroxyl group. You leave in the air for some time, you get this hydroxyl group. So what will happen? We have this, when you put this silane on top of this wafer, there will be a chemical reaction. So this part here, so the chlorine here, and this hydrogen here, they will come together to become HCl. So this one is the vapor, it's gone. So you leave behind oxygen here. So this oxygen here will be bonded to the silicon. So in that's why you see we have this silicon oxygen silicon bonding. Yeah, silicon oxygen silicon bonding. So this is how you bond to the substrate. But here you also see that you have also the lateral bond. You have silicon oxygen lateral bonding. So how to have this lateral bonding? This is because you have 3 chlorine, you have trichlorine, 3 of them. So how does this thing work? It's like this. We have the one silicon here, chlorine. You have another one, nearby one, silicon here, chlorine. So in the environment, there is always water. So water, we know it is like HOH. It is HOH. So effectively, this H will take away this chlorine to form HCl. This H will take away this chlorine to form another HCl. So in the end, you leave behind this oxygen here. So this oxygen will come to here. So you have this oxygen here. They have this silicon oxygen silicon that you can see here. So silicon oxygen silicon. So effectively, you form 2 HCl molecules to take away the chlorine. Then you have the oxygen bond. So normally you clean the wafer. Then you put the wafer a drop of the silane. So this silane is a liquid. You put a tiny drop, maybe microliter, a tiny drop inside the container and pump, vacuum the container. After several hours, you take it out, you do the baking, you get a very high coating property. And you make the surface very hydrophobic. So some of you may know we have this nanorobotics group. In one University of Waterloo, we have this nanorobotics group. So the task for the nanorobotics group is to move micro objects as fast as possible and pass the barriers. You move the object, very fast. When you want to move the nano or macro object very fast, you need the surface to have very low surface energy, very low friction force, very low surface energy, very low friction. And then the people that come to my group, come to me, maybe this happened maybe 7 years ago, they asked me how to make the surface very low friction. I told them to do this kind of process. Then later on, they won the first prize in the nanorobotics competition in the world. But this is the most important secret for the nanoimprint lithography. But nowadays, everybody who work on a nanoprint, they know about this coating to make the surface very low surface energy. So now let's look at the nickel mode. So for the nickel mode, we know that silicon mode, the silicon oxide mode, the problem is they are very brittle. It's fragile. It break easily. So the metal mode is not brittle. It can be used for many times. Actually, for the CD or DVD or Blu-ray, so they are made by using a metal mode by the injection molding process. But the metal mold is more difficult to fabricate, costs about $10,000 at least. Takes some days, 1 day or maybe even longer, to plate very thick layer of the metal. So here's how you make it. So first, you create the pattern. And this pattern here is done by the hot embossing. Hot embossing, you remove the ready layer, so you have the pattern. But this layer here, this is the seed layer, connecting metal film, metal connecting layer. You need a connecting layer for electroplating. Then you do the electroplating, you overplate, you prick the backbone, which is hundreds of micrometer thick. So this takes a day or maybe even longer time to do the plating process. Another problem is that so the edge plates faster than the central part. So you can imagine when you have more ions, come here. When you do the plating, you got more ions to the wafer edge than to the wafer center. So the growth here will be faster than the growth on the wafer center. You need polished back. You need polished back process. Another problem is that the nickel is not very good for the anti-slaking coating. So what you can do, you coat the layer of silicon dioxide, then you can do this process to make the surface a low surface energy. And this is the nickel mode. So this example gave you the soft PDMS mode. So here we have the rigid back plane, and we have this flexible PDMS. This is the elastomer flexible. On the top, we have this also rigid PMA. So we know that for the PDMS, the Young's modulus is about megapascal, a few megapascal. But for the PMA, for the PDMS, it's a few megapascal. For the PMA, it's a gigapascal, 10 to the power 9 pascal. So the Young's modulus is much higher than a PDMS. So you can have very high resolution features. But here you can see you have this mode. After imprint, you get the pattern into the resist. Here it's done by using the UV imprint at very low pressure UV imprint. But the problem is that the PMA is not compatible with this process. You cannot make the surface low surface energy. As a result, maybe after one imprint or maybe two imprint, the mold there will be lots of peel off. But this one in that is not good. It's only good for maybe one or maybe two time imprint. Then there will be peeling off problem because this one cannot be made a low surface energy. This one is good. This one you can have very low. You can have this anti-adhesion layer give you low surface energy. This one, the backbone is the PDMS. This is a plastic, soft plastic. So because it is plastic, so you can do the imprint onto the curved surface. You can see here, you do the imprint on the optical fiber because the PDMS it is flexible. It's very very flexible, soft. So how you make this mold? So first you coat the carbon agent and the coat the imprint resist. So this is the PDMS. You coat the carbon agent. Because the resist has low surface energy, we have a carbon agent. You get better adhesion of the resist onto the PDMS substrate. Then you do the UV imprint. This layer here is the UV resist. This layer here is the UV curable resist. You do the UV imprint, they separate, you get the mold. So you can see, not hard, it's not difficult to do to copy the mold from the master mold, from this master mold onto this polymer mold. So here the mold material, this one is the UV curing resist. So we know that for the UV resist, it contains silicon, has lots of silicon inside. Then if we do the oxygen plasma treatment, the surface will become a silicon oxide. So when the surface becomes silicon oxide, you can do this process to make it a low surface energy for imprint. That's why this is a very good mold. That's why it's published in the Nano Letters, very good journal. So this is the fluoropolymer mode. So we know that normally to save the master mode is very difficult and expensive to make. So to save the master mode, so we can copy the master mode into a polymer mode. Then we use the polymer mode as the to do the imprint. So the good polymer is the fluorocarbon polymer. This polymer is good because it has a very low surface energy, for the easy separation. But Teflon is not very good, and we will see later on it is difficult to copy the mold into the Teflon. But fluorocarbon, the other fluoropolymer is good. So this process, even though this process it works well to give you low surface energy, so the issue is that so when we do the UV imprint, we do, for example, free radical. We do the free radical polymerization. We have lots of free radical. But we know that the free radical is very reactive. Those free radicals will damage this self-assembled monolayer. As a result, after maybe 10 imprint, you need to coat the self-assembled monolayer again. So because of the free radical, when you do the UV imprint, you generate a lot of free radical polymerization. This is not good for this one. So as a result, ideally, we want the mold has low surface energy, then we do not need this self-assembled monolayer. This way, we can use the mold hundreds of or even thousands of times. So this is the idea here. So we have the mold in fluoropolymer. You can see this one. It is fluoropolymer, so this give you low surface energy. So in this paper, the mold is copied this way. So we have this silicon master mold. This is the this one is the pre-polymer. So it is a liquid. This one is a liquid. So because the fluorocarbon has low surface energy, so adhesion of this material onto the silicon mold, onto the substrate is not very good. So what do we need? We need this coupling agent. We have this coupling agent, adhesion of this pre-polymer to the substrate will be better. Then you press the mold onto it, then you do a thermal process, you anneal it at a high temperature, then it becomes annealed and solidified. Then you get the mold. But this is what published in this work. So at the present, I learned recently that at the present, actually for the mass production, using imprint, but this kind of polymer is actually used for the polymer mold. But this kind of thing is not published. The people don't publish so much. But this, I will talk to the people from the company. They can tell you this kind of information. But the substrate here, so in this work, the substrate here is silicon. But for the mass production, we don't want silicon. So what it is the PET sheet, a 10 micrometer PET sheet, rather than the fragile silicon. Another difference is that this layer here, in this case, this is cured by the high temperature. But for the production of the polymer mold from the master mold, it is cured by the UV imprint lithography, not by the thermal lithography. So that means the photoinitiator is added to this material rather than a thermal initiator. So for this work here, so we added the thermal initiator into this material. But for the UV imprint to copy the mold, we use the photoinitiator mixed with this material. Then you can cure the mold by UV light. So again, this is for the mass production, very, very important process. Here are a few other mold materials. The first one is the polyvinyl alcohol. You have alcohol here. This one is soluble in water. So you can copy the mold from the silicon into this material. Then you can use this material as the mold to do the imprint. Then afterwards, you can dissolve the mold. So this is the one-time use mold. This one is Teflon. So we have talked about this. This one obviously gives you very low surface energy and also very stable at high temperature. So it's stable at more than 250 degrees. So it is good for the thermal imprint and also for the UV imprint. But the problem is very difficult to make the mold into this material by the hot embossing process. So I have done once. So after you print the silicon mold onto the Teflon, then you cool down, so the mold become, the sheet got bended, not good. It got deformed, not very good. A better material, this one, ETFE, is ethylene tetrafluoroethylene. So this one have the fluorocarbon bond here, but here the hydrocarbon bond. But this one is easier to copy to make the mold. The last example is the SHQ, COC-coaxium. This is similar to HHQ. We know this one is the resist for the electron beam lithography and also for the X-ray lithography. This is the resist. So here it's similar, but we use it as the UV imprinter resist. But this material, after cross-linking, it is like a silicon oxide. So if it is like silicon oxide, it is good for this process. It is good to make the surface a low surface energy for many time imprint. So here I mentioned again, in principle, all the cross-linked polymers can be used as an imprinted mode, but in reality, most of them are not good for the mode release agent. You cannot make it low surface energy, but this material here, you can make it low surface energy. It's compatible with the mode release agent. Last example is the mold from the fly, the wing of the fly. This material here, you can see the wing of the fly have this kind of structures. This structure is, the period is 190 nanometer, the height is 400 nanometer. This give you the super hydrophobic property of the wing, making the surface very hydrophobic. Some researchers found out that this wing is actually a good material for the imprint. As you can see here, you can even do the thermal imprint at a pretty high pressure and a very high temperature. Very high temperature and high pressure to do the imprint in the PMA. We know PMA is not so easy to do the imprint because it has high surface energy. It's hard for the separation. But for the wing, for this wing, so first it is stable. It is very stable at a high temperature. Secondly, the Young's modulus is a gigapascal. It is similar to the PMA, but here the PMA gets melted, so it becomes soft. But this one is, you get 7 to 9 gigapascal even at higher temperature. More importantly, there is a layer of the wax, on the wing. As a result, the wax has low surface energy, so it's easy for the separation. That means the wing is naturally, it has the kind of anti-snaking property. So we have anti-snaking, we have low surface energy combined with another structure, you get a super hydrophobic. So the water will fall off, will fall off. This is good for this fly. So now let's look at alignment for the imprinted lithography. So there is a big challenge for the imprinted for the alignment for the imprinted lithography because first so we have smaller error budget. For the case of imprint, so we know we have this 1 times error. That means if the misalignment is 10 nanometer, then you get an error of 10 nanometer. But for the optical lithography, you have 4 times reduction. If we have misalignment 10 nanometer, it will become a 2.5 nanometer. The big problem for the imprint is the mold, distortion, and the drift because you need a high pressure. When you have high pressure, it's very hard to keep there may be some drift, and this will damage the alignment. And also the temperature. Then you have the thermal expansion mismatch. For the thermal imprint, it's very difficult because of the thermal expansion mismatch. For the UV imprint, it is easier, but still very difficult because of the high pressure. As a result, normally when we do the imprint, we do not do alignment. We just do 1 layer, then it's done. It's done for the devices. But in principle, you can do the alignment. It's just not as easy. In the example here, we got 10 nanometer alignment by doing imprint. But this one, in reality, is not so reliable. Sometimes if you have very bad luck, you don't get good alignment. So how to do the alignment? So one method is to use normally when we do the optical lithography, we use this kind of alignment. This is called cross alignment. For this cross alignment, you have this alignment mark on the mold. You put the complementary pattern, you have put a square here. You put the 4th square here. The other pattern on the 4th square, then you measure them, you get the alignment. This will give you about half micrometer alignment accuracy, which is not good for the nanoimprint. For the nanoimprint, we want, some 100 nanometer alignment accuracy. So how to do that? The one way is to have the grating. You put the grating on the mold, you put the grating on the wafer, they have the same page, you shine the light, you do the detection, you would transmit the light. In this case, we measure the zero order diffraction. So when they are aligned like this, you get the maximum signal here. You get the maximum signal. So we can also do the first order alignment. When we do the first order diffraction, so you have the laser light coming in, you get one to the left, one diffraction to the right. So you measure the distance. So when they are symmetric, when they are good aligned, you get the minimum signal. When they are aligned, you get minimum signal, zero signal. That's one way to do the alignment. We use gratings. The shift, the relative position of the two gratings tell you the misalignment. Another one we can use is called Moahe pattern. What is Moahe pattern? So this is the we have two periodic structures. When they are misaligned, you will see some larger feature set will show up. This is the Moahe pattern. So we will see this one later on. So the strategy is that first we do the coarse alignment using the optical lithography method. Then we do the fine alignment using this Moahe pattern. Here is one example. You have this concentric ring with the pitch P1. You have the same thing, which is the same pitch, also P1. Then you put them together. This one is aligned. When they are aligned, you see like this pattern. When they are misaligned, you see something like that. So a small misalignment, you can see this thing will show up. This effectively, you can. The misalignment is magnified. The misalignment is magnified by this Moahe pattern. If you look at the pattern here, if you look at you look at different angle, you see the like a wheel is to the rotation. This is because the screen has the pixels. So the pixel can also form the Marie pattern with this periodic ring structure. Here's the experimental setup. So you have the light come in. You have the partial reflection mirror comes to the sample. You have the one grating on the mask, another grating on the substrate. This one is P1, this one is P2. So the pitch is not the same. It's slightly different. Then the light come back from the grating, go to the CCD camera, you form the image. So here is one of the design. So here you have the P1, P2. So this P1 will match with the P2, and P2 match with the P1. But when they are aligned, you see something like this. When they are not aligned, you see something like this. So minor misalignment, it will show up as the grating. So the pitch here, the P1 and the P2, they're very small pitch. But the P3, the pitch is from here to here. This is the pitch. You can see the pitch here is P3. This one is much bigger than P1 and the P2. It is given by this formula, P1 times P2 divided by P1 minus P2. If the pitch here, the P1 and P2, they're very close, then this number is very small. You get a very big P3. That's why I said, effectively, the misalignment is magnified by this factor here. So here is another way of the design. This is the pattern on the mask. This is the pattern on the substrate. You flip the mode. You flip it over. So this P2 will come to the P1. P1 will overlap with the P2. Then you get something like this. When they are aligned, you see something like this. When they are not aligned, you see something like this. Again, the pitch here, the P3, from here to here. The distance here, this is the P3, is given by this formula here. P1 multiplied by P2 divided by P1 minus P2. Now let's look at how to derive this formula here. Here we have the dark and the bright. Where is the dark? Where is the bright? As you can see here, in this case, we are grating on the mode, grating on the substrate. As you can imagine, when you have this kind of alignment, so the light can pass through. So this is the bright, the bright. When you have this kind of alignment, so the light will be blocked. But this is the dark. This part corresponds the dark. But this part here corresponds the bright. So the pitch here is from here to here. This is the one of the pitch is the P3. This is the P3. As you can see here, in this case, so P3 equal to 7 times P1 equal to 6 times P2. So we have the 1, 2, 3, 4, 5, 6, 7. We have 7 times P1, 6 times P2. In general, the P3 is given by n times P1 and also n minus 1 times P2. From here, these two, we get n equal to this value. You put this n into here. So P3 equals NP1. You get it here equal to this one. This is the formula you get. The same one as this one, and also the same as this one. So this is how you do the alignment. And now I will show you a video I will show you a video for this Moahi pattern. It is a fun video. So the Moahi pattern here, you have as I said, you have two periodic patterns. The two periodic patterns, they do not have the same period. Then when they overlap, you see the pattern, magnified pattern. So now we look at imprint into the metals. Imprint into metals. In this first example, we do the imprint into the silver. We know that silver has very high, not very high, has a melting temperature of about 962 degrees. This is the melting temperature for the silver. But here the imprint is done at lower temperature, 400 degrees. But the pressure is very high. They use the 300 megapascal pressure. So normally when we do the thermal imprint, we only need 2 megapascal. But here the very high pressure, moderate temperature, and very high pressure. So this is the mold. This is the silicon mold made by the silicon using the deep RE. This deep RE, again, you see the wavy structures. So this uses the Bosch process. Use the Bosch process to make this mold. So because this one, the set one is rough, and also we have this, negative taper angle. As a result, the separation will be very difficult. In this case, the mold is not separated from the silver. It is actually dissolved. So the mold is dissolved by the QH etching. This way you get the silver pattern in the end. This is the demonstration to show that it is possible to do the imprint into the metal, but either you need very high temperature or you need very high pressure. So that is not easy. So in this example here, so we use the metal nanoparticles. So we know that for the case of gold, the melting temperature is a little bit higher. The melting point is a little bit higher, 1,000 degrees. But we have the gold nanoparticles. For example, here you have the gold nanoparticle, maybe 2 nanometer. But we have 2 nanometer here. You get the melting temperature is much lower. In this example here, you get 150 degree melting temperature. But this one is the resistivity. So you have the gold nanoparticle. They heat up to 150 degrees. Then the gold nanoparticle, they get connected, they get merged together to form a continuous film. And when you form a continuous film, you get low resistivity. And also you get a very high reflectivity. Will form the gold film at 150 at this temperature. For the last example here, we have the gold nanoparticles here, but it has the ligand. We have the RS group, as the cell R group. We'll heat up to nearly 190 degrees, maybe 190 degrees. This molecule RS is dissolved. You have the weight loss. But we cannot do imprint. So in principle, we cannot do imprint at 150 degrees, because if we do the imprint at 150 degrees, the particles they get merged together. But once they get merged together to form the film, the melting point go up right away. So it no longer melted. So what we can do? So we dissolve the nanoparticle. We could dissolve nanoparticle into a solvent. In this example here, so the solvent, this organic solvent is very special. It's very, very viscous at the room temperature, but it becomes flowable at 80 degrees. So what do? You dissolve the nanoparticle in the solvent. They have this soft PBMS mode, flexible soft mode. You heat up to 80 degrees and you apply a little bit of pressure, 5 psi. The psi is the pound per square inch. So we know each pound, the pound for is each pound, this kilogram, 10.8, 0.9.8 times 9.8. This gives you the force in how many Newton. So this is 14 pounds per square inch. This atmosphere is 14 pounds per square inch. So here you have 5 psi. Then you have the pattern into this solvent. You dry away the solvent, you leave behind the dried nanoparticles. Then you heat up at 140 degrees. Then the nanoparticles they get merged together, get merged together, you get the gold film, you get the gold pattern. You may wonder, how come we get this sharp corners? We have the metal, If the substrate, we have the metal, gold. If the gold got melted, you have something like a ball, right? Because of the surface tension, the melted gold should have this spherical shape. But in this case, it is melted, but for momentarily. So we have the nanoparticle, it got melted. But once they got melted, they come together, you get this big gold. It's no longer nanoparticle, so the melting temperature go up right away. That means the melting point here is 140 degrees, but once it got merged together, the melting point become, the melting temperature become, more than 7 degrees. That's why I said you cannot do imprint into the gold at 150 degrees, because once they got merged, the melting point go up right away. It no longer flow. In this example here, so we can do the imprint into the metal. We can do the imprint into the metal using the pulse, laser pulse. So we know that it's hard to melt the metal, you need a 7 degree, but it can be easily melted by using the laser pulse. So the example here, we show the imprint into the bulk silicon. This is not metal, it's not metal yet, it's silicon. But we can do the same thing on the metal. Here you can see, first we press the mold onto the silicon substrate. Then we shine the laser light, pulse the laser light, so the top layer will get melted momentarily for nanosecond. The top layer got melted. Then the mold gets sink into the substrate. Then cool down, you separate, you get the pattern. This way, you can pattern the silicon at one shot. This happened only within 100 nanoseconds. This paper is published in Nature in 2002. You may wonder what's the importance for this. So normally, when we make the structure in the silicon, so we need to do the lithography. We need to pattern the resist patterning by lithography. We do the pattern transfer. Then we remove the resist. We need the 3 steps to do the pattern transfer to the silicon. But here, we only do 1 step. Just shine the laser, you pattern the silicon right away. And this is done within 100 nanoseconds. So this is very, looks very good. That's why it's published in Nature in 2002. But the problem for this one, so at the beginning, people think this is really important. So maybe you can pattern the silicon used for the IC. You can pattern silicon for the IC manufacturing. But the problem is that later on, people found out that we have this molten silicon that's solidified. It is cooled down very fast. The silicon here, the top layer here, become amorphous. It's no longer crystal. It becomes amorphous silicon, or maybe polycrystal silicon. We know amorphous silicon, a polycrystal silicon, are not very good for the device. They have a lot of defect and very low mobility. So we can do the similar process using metal. The idea is simple. You coat the metal film on top of the silicon substrate. Then you do the same process. So the metal can be melted by the laser pulse. Here in this case, we use the xenon chloride laser. This is the excimer laser. So by far, you should be very familiar with the excimer laser because we know that for the lithography, the 193 nanometer, this one is the argon fluoride excimer laser. This for the IC manufacturing. For the xenon chloride, you got 308 nanometer. The pulse duration is 20 nanoseconds. This power here, 0.24 joule per centimeter square, looks a very low number, but it is only 20 nanoseconds. So you divide this number by this number, you get 12 megawatt power. This is very high power. That's why you got melted. The top surface got melted. Then you get the metal grating structures. But here the surface become rounded because of the shrinkage upon the solidification of the molten metal. So now let's look at how big feature, how much pressure we need. So how much pressure we need to do the imprint. So we have seen this example here. So this example we have seen before. The pressure is given by 2 times gamma over R. This is to we have the hole. We have the hole in the mold. Now here we have the trench. We have the trench in the mold. So the pressure can also be calculated. So here the force. We have this. The force here. Force here. This is the surface tension force. The 2 times left, right. We have 2 times the weight gamma L divided by the area. So the area. This is L. Area is WL. Then you get the pressure 2 gamma over W. So what will happen? Then we have the liquid already touched the bottom. Your liquid already touched the bottom. How to calculate the pressure? The pressure you need to touch the bottom with the gap here is R. This is the R value. And this is not so straightforward, but it's not hard to understand. So what do you do? First, you can consider this volume of the liquid. So you consider this volume of the liquid. Then we consider the force along this direction. The force along this direction here. So what the force you have here? So the drawing not so good. So this one should be parallel to this overlap with the dashed line, but the drawing here is not so good. So you have this force here. So this one you have gamma L force here. Another one here gamma L, right? Then you have the force from the liquid. The liquid here will exert a force onto this surface. And this force here is given by pressure times area. The area here is given by this part, the square root 2R times L. So the force here is P square root 2R times L. This is force. In the end, the force should be balanced. That means this force here, P equal to 2 gamma. So 1 gamma L here, another one here. You have 2 of them times cosine 45 degree. Because here you have the force. This force point up, this force point here. Along this direction, then we have this 45 degree here. So here you can cancel out the arrow. But this one cosine 45 degree. This one, right? Then you get, in the end, you get this formula here, gamma over R. As you can see here. So P times square root 2RL. So this one equals 2 gamma L cosine 45 degree. You get this formula. So this is one way to calculate the pressure. So we can also do another different method. For example, you can also consider the volume. Consider this volume here. Draw a line here. So consider the volume here. We consider this volume of the liquid. But now we will figure out what is the force. So what force we have here? So we have the force from the top part of the liquid. So we have this force here. And this force here is given by a pressure times area. Area equals WL. So this is the weight here. So this is the W. So this is the force from the top. So then we have this force here. Again, gamma L here, another one here. another fault here. This is also gamma L. So then we have the force from the bottom. So this, the bottom of the mold will give another force into the liquid, into this particle of the liquid. But this one is given by a pressure is the same. The pressure in the liquid is the same times the area. So the area here, the constant area here is equal to W minus 2R, right? So this is the W here. We have 1R on the left, 1 on the right. W minus 2R times L. So the forces, the four forces here. So this one downward, this one upward, this one upward, this one also upward. This should be a balance. That means so P, this one equal to 2 times plus P minus 2R L, right? This is what you got. So we can do some simplification. We can do some simplification. So this term here, PWL is cancelled out with PWL. So it's this one cancelled out. So in the end we get, we move this part to the left. So we have P2RL equal to 2 gamma L. Then you get the pressure here. So the pressure here, again, is given by gamma over R. You can see it's not so hard. So what do we do? So we consider this volume of the liquid. Then we do the force balance. We can see another example here. We can have another example here. What happens if we have a pillar remote? So we have the mold like this. They are protruded pillars. This is the side view, the top view, like this. They are pillars. So we have the two-dimensional pillar array. So how to calculate the pressure for this kind of situation? So this again. So we have here. We take one pillar here. There's one of the pillars. We take this one pillar. We take this one pillar. Then we have the liquid filling here. We have the liquid. This is the substrate. So we consider this volume of the liquid. So we consider this volume of the liquid. So then we balance the force. So here we have this one is downward. This one is also downward. So they are hydrophobic. They do not wet. So the force is downward. So from the bottom, we have this P times say L. From here to here we see W, maybe say W squared. So P W squared. So this is the force from the bottom. From top, here we have this force here. We have also this force here, But this is given by P times. If this is the circular shape, we have pi squared. So in the end, the force, the force by the pillar top is given by this one, gamma L equal to P times W. W is the period, this area here. Again, this way we can get the pressure. So here, how much pressure we can get? So we know we have seen this formula before. So the maximum feeder size is given by this formula. For the case of the imprint into the metal by using the laser pulse, so the pressure here we use very high pressure, 400 atmosphere pressure, very high pressure. The time here is the pulse duration is 20 nanoseconds. The pulse is 20 nanoseconds. But actually take about another additional 80 nanoseconds for the liquid, for the metal to solidify. The total time that the metal is in the molten state is 100 nanoseconds. So the film thickness is 200 nanometers. Then we need to know the viscosity. So the viscosity of the metal, the viscosity of the molten metals is similar to that of the water. Similar to that of water. For the case of water is 0.00091 pascal second. So the viscosity for the metal is in a similar range. So we put everything together, we get this number. But in reality, for the silicon, the theoretical, this formula predicts we can get 12 micrometer feeder size. In reality, the 17 micrometer silicon can be patented, but higher, if we have 10 micrometer, the time, the 100 nanosecond will be too short, so this will not work. So thank you.